Hey, Dr. Clark coming back at you with another Check Your Understanding video. We're in section 8.3, which means we're looking at forced linear systems, okay? And the problem they've given us here is it's an applied problem or a modeling problem. So let's read through it and then we'll take a look. So we have a spring mass damper. Mass 1 kilogram, a damper provides a force in the opposite direction of motion equal to 8 times the velocity, a spring that stretches 1 meter under a 15 Newton force, and a decaying external force of 6e to the negative 2t. Okay, so if you model that as a differential equation, you get this. So they give you the model, x double prime plus 8x prime plus 15x equals 6e to the negative 2t. But all of this could have been written as that model. And then the mass is released from rest at position 2 units to the right of equilibrium. So the idea here is you've got a spring mass damper set up, and that mass is going to oscillate left and right, but there's an external force, F of t, pulling it to the right at 6e to the negative 2t newtons of force, and then we have that initial condition, x of 0 being 2 and x prime of 0 being 0 because it's released from rest at position 2 units to the right. And x of t here is that position function, okay? X prime of t would be velocity. And the way they want us to solve this is to write it as a matrix vector initial value problem in y. So they want us to think, instead of just solving for x, they want us to solve in terms of state space. So that y vector is going to be position, velocity bundled up together into a state. Okay? And that means, well, if we do a little bit of thinking here, we know that x prime is equal to, let's call this xy, okay? So let's let y be the velocity and x be the position. Then x prime is equal to y, and y prime is equal to x double prime, because the derivative of velocity is the second derivative of position. And if we look here, we can see that this can be solved for x double prime. So we can subtract this 15x over, we can subtract that 8x prime over. So let me subtract those over. And then we have 6e to the negative 2t already there. And one more step. X prime was already described as being y, so I'm going to write y in the place of x prime. And there's my external force. So now I can write the differential equation as a vector differential equation, d capital Y dt, and I can write it as a matrix negative 15, negative 8, or sorry, not negative 15, negative 8, 0, 1, negative 15, negative 8, multiplied by xy here, because here's xy times 0, 1, that gives you y, x prime equals y, that's in the top row. And then negative 15, negative 8 times xy gives you that negative 15x, negative 8y right there. And then we have an external force, which is 0 on the x, because x prime equals y, and then 6e to the negative 2t. That's the force shows up in the bottom row, because the bottom row is acceleration, so that's when the forces show up. And then the last step is to replace this xy with state vector y, because xy is state vector y. And then the initial condition, y of 0, is position 2 and velocity 0, so position 2, velocity 0. That is my initial value problem, so that is the answer to part A. Write the system as a matrix vector initial value problem. And notice this here we usually call f of t. That's an external forcing term. So, you know, you have y prime equals matrix y plus external forcing term. Like so, this is sort of the generic form we're looking at. Vector y prime, matrix A, y, forcing term f. Okay, the second question says use the eigenvalues and eigenvectors method to find the homogeneous solution. So what you want to think of is the general solution is going to be a homogeneous solution plus a particular solution to the non-homogeneous problem. And so for part B, we want to find that homogeneous solution. And to do that, we need the eigenvalues and eigenvectors of the matrix. So we're essentially solving y prime equals that matrix, 0, 1, negative 15, negative 8, times y. And we're ignoring the forcing term. We're just solving the homogeneous problem. So let's do that. So we subtract so to find that we need the determinant of A minus lambda I, where lambda is the eigenvalue, I is the identity matrix, and A is the matrix 0, 1, negative 15, negative 8. So we got negative lambda, 1, negative 15, negative 8 minus lambda. Take the determinant, we multiply the diagonals down. And we set that determinant equal to 0. And if we multiply through, we get this quadratic equation, and it looks like this thing can be factored into lambda plus 5, lambda plus 3. So lambda equals negative 5 and negative 3. Those are those eigenvalues. Okay? Once you have the eigenvalues, you can find the eigenvectors. So the matrix, again, is 0, 1, negative 15, negative 8. If we multiply that by some vector AB, we should get negative 5 times AB. In other words, that's the definition of an eigenvalue eigenvector pair. Matrix times vector equals number times vector. So this vector is only being scaled, not rotated. And to do it, you can just look at the top row. The bottom row will be algebraically equivalent. The top row is b equals negative 5a. And so a vector that satisfies that condition would be the 1, negative 5 vector. I'm going to call that v1 for eigenvector 1. Okay, and what I mean by that is if a is equal to 1, then b is negative 5 times a, or negative 5. Or if you take negative 5, or 1 negative 5 times this matrix, you'll get negative 5 times 1 negative 5. All right, and similarly, if we solve the same problem with the other eigenvalue, negative 3, then that top row is just b equals negative 3a, and so 1, negative 3, that'll be eigenvector 2. And we can use the eigenvalues and eigenvectors to construct that solution, yh of t, the homogeneous solution. What is it? Yh of t is c1 e to the lambda 1 t times eigenvector 1 plus c2 e to the lambda 2 t times eigenvector 2. And that is the homogeneous solution to this differential equation. And that's the answer to part B. Part C asked us to use the method of undetermined coefficients to find a particular solution. In other words, guess an answer and figure it out that way. Well, the forcing term is an e to the negative 2t function. And since it's a linear system, if y is an e to the 2t function, when you multiply it by a matrix, you'll get another e to the 2t function. Take the derivative of an e to the 2t function, you'll get an e to the 2t function. So basically, we're just going to guess y to be some e to the 2t function, or e to the negative 2t function, rather. So I'm just going to copy this differential equation here, and we'll paste it down for part C. In other words, we're going to guess that yp of t is some e to the negative 2t function times ab. I don't know which e to the negative 2t function, but some vector e to the negative 2t function. If that's the case, then y prime would be negative 2 e to the negative 2t times ab. That's the left-hand side of that differential equation. The right-hand side says take this matrix A, multiply it by y, and then add that to it. So if I take the matrix 0, 1, negative 15, negative 8, and multiply it times my guess, e to the negative 2t ab plus 0, 6 e to the negative 2t, the forcing term right here. Then on the right-hand side, I will get e to the negative 2t times the vector, what is this, b, and then negative 15a minus 8b. That's just multiplying row times column, and e to the, that's just constant that comes out front. And then this will become e to the negative 2t times 0, 6. And when we equate the left-hand side with the right-hand side, you'll notice they all have an e to the negative 2t in them. So we can cancel out the e to the negative 2t's and just set the vectors equal to each other. So the left-hand side is negative 2a, negative 2b. The right-hand side is b, negative 15a minus 8b plus 0, 6. And this is somewhat convenient because b equals negative 2a is the top row, so we know what b is. And so I'm going to substitute that into the bottom row. On the left-hand side, I will get negative 2 times b, which I just noticed was negative 2a. So that's equal to 4a. On the right-hand side, I'll get negative 15a minus 8b, and b is negative 2a, plus 6. So now I'm solving 4a equals negative 15a plus 16a plus 6. 3a equals 6. A equals 2 is the solution, and therefore b is negative 4. So now I've done the algebra, found a is 2, b is negative 4, and that means that I can write down the particular solution right here as e to the negative 2t times ab, and a is 2 and b is negative 4. So 2, negative 4, that is my answer to part C. And finally, the last question says solve the initial value problem. Well, we know that the general solution is the sum of the homogeneous and the particular solution. So we've done B and C, we've constructed the particular, we've constructed the homogeneous. We can write down the sum and then solve for the initial condition, which was 2, 0. Okay? And so we have our general solution is the sum of that homogeneous solution right here. Let me just copy that down. And we will paste it here. So that's the homogeneous. We just found that particular solution right here. And so the sum of them will be the general solution. So YG, general solution, is YH plus YP. Now, I don't want the general solution, I need the initial condition. And the initial condition was y of 0 equals 2, 0. That was the initial value problem here. And so I'm just going to plug in 2, 0 on the left-hand side and plug in t equals 0 here, here, and here. And when I do that, I'll get C1 times 1, negative 5, rather, plus C2, 1, negative 3. So this is what happens when you plug in 0 for t. E to the 0 is 1, e to the 0 is 1. So you just get C1, 1, negative 5, and C2, 1, negative 3. And then that particular solution, again, e to the 0 is 1, so you'll just get 2, negative 4. And this means, if I do a little bit of algebra here, 0, 4 has to equal C1 plus C2 and negative 5 C1 minus 3 C2. It appears from the top row that C1 and C2 are equal to each other, but in opposite signs. And I believe if we set, we'll just say that C2 is negative C1. And so 4 is negative 5 C1 minus 3 C2, which is negative C1. And that means that 4 is equal to negative 2 C1. So C1 is negative 2, and C2 then would have to be positive 2, doing the algebra. And so now my final solution to the initial value problem is C1, which is negative 2, e to the negative 5t, 1, negative 5, plus C2, which is positive 2, e to the negative 3t, 1, negative 3. That is that homogeneous solution we just found, plus the particular solution, which is e to the negative 2t times 2, negative 4. And that will solve the differential equation and satisfy the initial condition, and therefore that is the answer to part D, the solution to the initial value problem that we constructed. Since this is equal to xy, the state vector y is equal to xy, then we could reconstruct x of t, which would be what? Negative 2 e to the negative 5t plus 2 e to the negative 3t plus 2 e to the negative 2t. That's the position of that spring mass problem. So you can reconstruct x of t using the state vector. We also know the velocity, but of course the velocity is just the derivative of x, so you could find it another way as well. So hopefully you were able to follow along. If you were able to solve that problem, that's great. That's a difficult problem with a lot of steps. But each of the steps is things that we've seen, and so we're building up big problems out of smaller pieces that we've done before. So we'll see you next time, and have a good day.